So in other words, here's what you can visualize here. If you have a positive source and a negative source, this is called an electric dipole. Wants to push this sucker northeast, let's say. The negative source wants to suck this southeast. And if I can get this exactly in the middle, which I'm having trouble because, there we go, the positive source and negative source, the north and south components of the force cancel out. So the net result is it's going to go which way? It's going to go to the east there, right? So if I turn on all my little visualization tools, at this exact point, the field is flowing to the right, to the east. So if I run this, you'll see that it's going to flow to the east there. And then, the field changes. So what's cool is the computer will model that. So in real life, this is a very important shape. This is called an electric dipole. If I let this sucker run, you can tell that this one's a positive source, this one's a negative source, because the field lines are flowing away from the charge on the left towards the charge on the right. Or in 3D, the way you can visualize this is we have an electric hill, because you generate a super strong electric field between the 2 points there, and you can store up a lot of energy and information. So what I liked about the Leyden jar example is we had a charged plate pair, but actually it was a charged plate dipole. There we go. The outer plate of Leyden jar became positively charged. The negative plate was negatively charged. So the inside of our Leyden jar, when we held it up to Van de Graaff, grabbed a lot of electrons. That's like the one on the right. The outer plate becomes positively charged because whoever was holding it is grounding it, so it gets an induced positive charge. You set up a super strong electric field between the two plates right in here. And then because of that, you can pack in a ton of charge, like you're stuffing it into the jar. So that's why even though the Leyden jar is so small compared to the Van de Graaff, this sucker packs a huge punch. At point B, what would a positive test charge feel from each of these charges? So the rule of thumb is, anytime you have two or more charges, you just add up each field's vector at each point, and you get a resultant sum. So what would the positive source do to the charge at point B? It would push it which direction? Straight up. And you're saying, well, how big should I make the arrow? Let's pick a side that's consistent with what we have here. Since it's closer than point A, it should be smaller or bigger. It should be, if it's closer than point A, it should be bigger, right? So it looks like that one's a centimeter. Why don't we make this one so let's make this like 4 centimeters to scale, something like that. So go ahead and label this force positive. And this has a force of 4. We don't have to write centimeters. We're just trying to scale it somehow. That's the field from the positive source. How about from the negative source? What's the field going to be? The field is going to pull it in what general direction? It's an attractive field, right? And if I line this up here, towards the center here, it's going to pull it towards the center, right? In the south, easterly direction. But the catch is, point B is closer or further from the negative source? Further. In fact, I'm going to go ahead and measure on my paper, and I'll measure here, and it looks like it's about 3.5 centimeters from the positive source, but from the negative source, it's about 6. So let's just say it's a 2-to-1 ratio to make it easier. So, in other words, this arrow should be smaller. If it's twice as far away, it should be 4 times smaller, or only a centimeter to scale. So in other words, the force negative is smaller than the force positive because it's further away. So how do I get my final resultant? Let me zoom in here so you can see what's going on. You can construct a quadrilateral shape where the opposite sides are parallel to each other. So I'm just going to take my ruler and sketch this in really quick. There's my parallelogram. This side is parallel to this side is parallel to this side. And the resultant is always where you start to where you end up. So in other words, using common sense, how's the field going to flow? It's not going to go north. It's not going to go southeast. It's going to have going what? In the northeasterly direction. You see that? This is my force resultant in the northeast direction. Okay? Actually, I should put the R down here. Force resultant. There you go. So why is it northeasterly? Because notice it's closer to the positive charge, but twice as far from the negative charge. So the net effect is, if I reset my simulation, if we're picking a point that's directly above the positive source and the negative source is further away, the southeasterly force is going to be a lot weaker than the north force. So the net effect is it's going to go northeast. So if you look at the field here, at that point it flows in the northeasterly direction. Okay? So to summarize what's going on, to visualize an electric field, we just have to realize that all fields have a size and direction. Direction depends on if it's positive or negative. The size depends on its distance for the strength there and the strength of the source there. And then we can apply vector rules to figure out the final direction by sketching in a parallelogram.